Right. Hello, everyone. My name is Fiona from the Pennsylvania State University, and in the Department of Civil and Environmental Engineering, as part of Dr. Lee's Reactive Water Lab Group. And in my series of videos, I'll be talking about nitrogen processes using the BioRT-HBV model. So to begin, I'll be walking through the general conceptual outline of the BioRT-HBV model. For folks that have already seen videos in this series, this may sound familiar or a general repetition of previous content. So if you're comfortable enough with the outline of the model, you are able to skip this portion if you like. For folks that are listening to this video series for the first time, so this will provide an overall understanding of how the model works. So to start off, the BioRT-HBV model is a coupling of two different types of model. The first one is a simple bucket type HBV hydrological model. And then there's the second type of the reactive model, BioRT. So combined, it will simulate stream discharge and stream chemistry. So from the HBV hydrological model, we can get flow partitioning of discharge from 3 different zones. So let me get my laser pointer out. So first zone that we have is a surface zone, which we are representing this as a quick flow in relative terms, where the flow is too fast for reactions to occur. So from the surface zone, we'll have water that will infiltrate into this shallow soil zone, where in relative terms, the water moves relatively fast through the catchment, but still has enough time for reactions to take place and interact with different solutes. In this zone, the water is majorly interacting with biogenic solids that are produced in the soil zone from biotic processes. So from there, some of the water will further percolate down into what we call as this deep zone, where it contains the long and deep groundwater flow paths that have a lot of time in the water catchment to react with different solutes and different mineral phase materials. So these waters tend to be overwhelmed with geogenic process solutes. So then once we have the hydrology, we then can implement reactions into these shallow and deep zones using our BioRT model. So for this video series, we'll look at the different nitrogen processes that are implemented in these shallow and deep zones and how we can use the BioRT model to actually simulate it. So we can start by looking at the nitrogen processes that occur in the shallow zone. And it's worth mentioning that the reactions that we're looking at in this video series are involved in tracking nitrate. And in the shallow zone, we'll be focusing on a soil and leaching process, as well as a plant nitrate uptake process. So to start off, we're going to looking at the soil and leaching process, which in general terms, we consider the soil and leaching process as a combined net effect of several reactions that will generate nitrate and deposit nitrate in the soil. This could include processes such as microbial decomposition of soil organic matter, nitrification process that converts ammonia to nitrate, as well as weathering nitrogen-rich bedrock, and which could release nitrogen into the shallow zone via rising of the water table. So in the BioRT model, we have reaction networks that represent each of these different reactions that we're looking at. For the soil and leaching process, we use an overall lump reaction network to represent the overall nitrate that is being released from this soil and process. This is because it's hard to tease apart which processes generate the different nitrates, nor do we know like a proportional fraction of what the nitrate production is from for the different pathways. So the reaction network that we use here is a relatively simple soil and solids to nitrate. Here, the soil and solid represents a bulk soil and solid phase material that can leach out nitrate, and that is being producing this nitrate as a product. So then after looking at the reaction network for soil and leaching, we must further understand the reaction rate law that governs this reaction. For our model, we are using the Monod rate law to govern the reaction rate for the soil and leaching process. which is currently shown here. So to break down what this Monod rate law is actually referring to, this R represents the reaction rate, and it is a product of all these combined effects. The first one, if we have, is the K term, which is the rate constant. And then we have the amount of surface area of the bulk soil and material that's available for the reaction. This overall term here is the Monod law that accounts for substrate limitation. In our case, for soil and leaching, this is the bulk soil and solid that we're referring to as our limiting substrate. If you can imagine, that really overall determines how much nitrate can be produced. And then we have our sensitivity functions for temperature and soil moisture. So these parameters can then later be adjusted and calibrated for more representative reaction rates for specific watersheds. The next process that we're going to look at in the shallow zone is what we consider as the uptake of nitrate by vegetation. We also use a relatively simple reaction network to represent this process that does not require a detailed understanding of all the mechanisms that are associated with the nitrate uptake by plants. So in this BioRT reaction network, here we have is this plant N solid, which is representing the biomass of plant roots. It is uptaking this nitrate by the plant and producing what we call it ON plant, which is representing the assimilated nitrogen that becomes organic N in the plant biomass. So in order to represent the rate of plant nitrate uptake, we are also using a Monod rate law, like the one that we use for the soil and leaching process. Here again is the reaction, the specific breakdown of the Monod reaction rate law, which we have the reaction rate or the rate of the nitrate uptake is dependent on this rate constant, the surface area, and then we have the Monod term again. And here we are indicating that nitrate is our limiting substance for this overall reaction to occur. As you can imagine, if nitrate is limiting in our soil, then our plant is limited how much nitrate it can take up and produce this organic N. And then once again, we have the sensitivity functions for temperature and soil moisture. So with an understanding of what these two BioRT reaction networks are and also the governing reaction rate laws, this kind of wraps up our first video with an understanding of sort of the background theories associated with some of the nitrogen processes that can occur in the shallow zone of a catchment. In the next video, I'll walk through how these reactions can actually be set up in the BioRT model and look at some of the results that can occur.